All right, let's get right into it. We're going to tackle a question that seems, kind of paradoxical. How can a tiny change in temperature, we're talking just 1 or 2 degrees, lead to these massive global consequences? It feels so small, but the impact is absolutely huge. So let's break down what's really going on behind that number.
So you hear these numbers all the time, right? The goal is to limit warming to 1.5 degrees Celsius. But what does that actually mean for us? I mean, a 2-degree change is barely something you'd notice walking outside, so why on earth is this tiny number such a gigantic deal for the entire planet?
You hear this phrase from climate scientists constantly, and it's not some kind of exaggeration. It's a serious warning. Today, we're going to figure out exactly why every single fraction of a degree is so critical, because the secret isn't in the number itself, it's in what that number is hiding.
And this, right here, is the key. A global average does exactly what it says. It averages everything out. It smooths over all the wild, intense variations happening all over the planet. So while some places are warming up just a little, others are heating up at a truly terrifying speed. The real story and the real danger is in those extremes.
And to really see this in action, we've got to look north, way north. The Arctic basically acts like the planet's refrigerator, but right now, that refrigerator's, it's breaking down. The data shows us exactly where the system is failing.
Now, okay, this chart might look a little complex at first, but the story it tells is actually incredibly simple and pretty alarming. It's showing temperature changes across the globe. See how those lines just spike upwards on the far right? That deep red zone over the Arctic? It shows warming that isn't just a little bit higher. No, it's in a completely different league.
And there's a name for what we're seeing here. It's called Arctic amplification. It's a really core idea in climate science, and it describes this exact thing. The fact that the poles, especially the Arctic, are warming up way, way faster than the rest of the globe. So let's put some hard numbers on that. Globally, we've warmed about 1.1 degrees Celsius. That's the average. But because of this Arctic amplification, the far north is getting hotter at least twice, and in some spots, up to 4 times that rate. The average completely masks this incredible reality. So what's going on? What's causing this supercharged warming at the top of the world? A huge piece of the puzzle is a powerful self-reinforcing cycle, a feedback loop. It's called the albedo effect. Okay, here's how it works. Step 1, you have this bright white sea ice that acts like a giant mirror bouncing the sun's heat right back into space. Simple enough. Step 2, as things warm up, that ice starts to melt and it reveals the dark ocean underneath. Step 3, unlike the reflective ice, that dark water just soaks up the sun's heat like a sponge. And that leads to step 4. The warmer water melts even more ice, which reveals more dark water, which absorbs more heat. You see where this is going? It's a vicious cycle that just keeps accelerating the warming.
Now, this whole idea of a breaking point isn't just some abstract thing happening to ice caps. It is deeply personal, because that same small rise in the global average temperature is pushing our own biology to its absolute limit.
For the longest time, scientific models and theories suggested that the hard limit for human survival, the point where we just can't cool ourselves down anymore, was something called a wet bulb temperature of 35 degrees Celsius. That's about 95 degrees Fahrenheit, but, and this is key, at 100% humidity.
But it turns out that theory was wrong. New experiments done with actual people at Penn State found that the breaking point is much lower. For young, healthy people, the real limit is just 31 degrees Celsius wet bulb. That's 87 Fahrenheit with full humidity. It means we are way more vulnerable to heat than we ever thought.
So what exactly is this wet bulb temperature thing? It's not just about heat. It's a measurement of heat and humidity combined, and it marks the point where the air is so full of water that your sweat literally can't evaporate. And since sweating is your body's #1 way of cooling down, that system just shuts down. It stops working.
And it's not just our bodies that have this problem. The very plants that make up the foundation of our food supply, well, they have a breaking point too. And when they cross that line, the consequences are just as serious.
So, check out this chart. It lays out the problem perfectly. On the bottom, you have temperature, and on the side, you have how much food we get from major crops like corn and soybeans. You can see the line goes up for a bit, it peaks, and then something really dramatic happens. Researchers call this the cliff edge effect. And it makes sense, right? For a while, a little more heat is actually good. The plants grow better and you get more crops. That perfect temperature seems to be around 29 or 30 degrees Celsius. But once you go past that sweet spot, things go south, fast. Yields don't just gently decline, they fall off a cliff. It's a total collapse that puts our food security at risk.
Okay, so let's tie all of these threads together. We started with this one small, kind of misleading number, that global average, and we've seen how it kicks off a whole chain reaction of really big problems.
So here's the domino effect we just walked through. It all starts with that innocent-looking global number. But that number completely hides the hot spots, like the Arctic, where feedback loops are putting warming into overdrive. That intense heat then pushes human bodies past their breaking point. And at the same time, it pushes our most important crops right over that cliff edge, threatening the entire food system.
What this all shows us is that the real danger here isn't slow, steady change. It's these sudden tipping points, these collapses that we're seeing in the Arctic, in our own bodies, and in our fields. So it leaves us with one pretty big question. If one simple average can hide this much danger, what other breaking points are we getting close to without even realizing it?